Hey everyone, and welcome to this Pharmacology Masterclass. Today, we are going to make absolutely sure you can perfectly answer a 25-mark university exam question on signal transduction. If you're an MBBS or MD student staring down those intimidating long essay questions, you are in exactly the right place. I'm going to walk you through this step by step, really unpacking the molecular mechanics of how drugs act in the body so you can walk into that exam room feeling totally unstoppable. Let's get started.
Here is our game plan for today. We'll kick things off with the macro concepts in signal transduction basics, then explore the 4 receptor superfamilies. After that, we'll spend a good chunk of time on the G-protein coupled receptors, dive into second messengers and signal amplification, touch on enzyme and nuclear receptors, and finally, wrap it all up with regulation and a tight exam summary.
All right, Part 1, Signal Transduction Basics. Let's jump right in by nailing down the foundational definitions you absolutely must put in your exam introduction.
So what actually is signal transduction? Well, basically, it's the journey of a single drug molecule translating its presence on the outside of a cell into a massive cellular response on the inside. It follows a highly specific, step-by-step sequence, and honestly, you should sketch this exact flowchart on your exam paper. It starts with a first messenger, which is your drug or ligand, binding to a receptor. This activates a transducer, which then signals an effector. That effector pumps out a second messenger, and boom, that ultimately leads to your physiological response. It's literally the fundamental language of pharmacology.
Now, what's really fascinating here is looking at the actual protein targets where this whole chain reaction kicks off. Drugs can target a few different things: receptors, ion channels, enzymes, or carrier molecules. But for our focus today, we are going to zero right in on the receptors and ion channels, because those are the primary structures that directly translate external chemical signals into internal cellular action.
Moving on to Part 2, the 4 receptor superfamilies. We can organize all these cellular targets based on their molecular architecture, and this categorization is going to form the backbone of your essay.
Okay, listen up, because this is a massive, high-yield exam point. If you get a long essay question on this topic, you absolutely must draw out a comparison table showing the drastically different speeds of action for these 4 families. We've got Type 1, the ligand-gated ion channels, which operate in a flash, just milliseconds. Type 2, the G-protein coupled receptors, working in seconds. Type 3, the kinase-linked receptors, which take minutes to hours. And finally, Type 4, the nuclear receptors. Those take hours to days because they literally have to alter gene transcription. Make sure you memorize this timeline.
Let's start with family number 1, the ligand-gated ion channels. You might also know them as ionotropic receptors. These guys are built for one thing, and that is pure speed, specifically fast synaptic transmission. Imagine a structure with a central water-filled pore. The ligand binds, the channel pops open in milliseconds, and ions just flood in or out. This causes instant membrane depolarization or hyperpolarization. Classic examples here are the nicotinic acetylcholine, NMDA, and GABA-A receptors. In fact, this pathway is exactly where drugs like benzodiazepines, barbiturates, and succinylcholine exert their incredibly rapid effects.
All right, Part 3, G-protein coupled receptors, or GPCRs. Honestly, if you only master one section today, it needs to be this one. It's the most important section for your university exams. Picture this, a single polypeptide chain weaving back and forth across the cell membrane exactly 7 times. That's the classic 7-transmembrane structure. Now, on the inside of the cell, it's coupled to a trimeric G protein, meaning it has 3 parts: alpha, beta, and gamma subunits. In its resting state, that alpha subunit is just holding onto a molecule called GDP. But the second an agonist binds to the receptor, it triggers this critical exchange, swapping out GDP for GTP. That is the spark. The GTP-bound alpha subunit breaks free from the beta-gamma complex, and they both rush off to activate their various target proteins. So, let's break down the specific pathways, starting with the GS pathway. And remember, S stands for stimulatory. Step by step, the drug binds the receptor, which activates the GS protein. The free alpha subunit then activates an enzyme called adenylyl cyclase. Think of this enzyme like a factory that rapidly converts ATP into our second messenger, cyclic AMP, or CAMP. The CAMP then activates protein kinase A, which goes around phosphorylating proteins to create a massive cellular response.
This cascade is exactly how adrenaline acts on beta receptors, how glucagon functions, and how asthma drugs like salbutamol cause life-saving bronchodilation.
But you know, the body loves balance, right? This beautifully illustrates how our physiology regulates itself, contrasting that stimulating GS pathway with the inhibiting GI pathway. While GS boosts CMP production, the GI pathway, which is triggered by things like M2 muscarinic receptors in the heart or alpha-2 receptors, actually hits the brakes. It actively inhibits adenylyl cyclase, dropping CMP levels and leading to opposite clinical effects. This mechanism is super relevant when you're talking about drugs like clonidine or opioids.
Then we have the GQ pathway. For your exam, you absolutely need to write out this specific cascade. Here, the GQ protein activates a totally different enzyme, phospholipase C. This enzyme acts like a pair of molecular scissors, cleaving a membrane lipid called PIP2 into two distinct second messengers, IP3 and DAG. IP3 rushes straight to the endoplasmic reticulum and acts like a key, unlocking massive amounts of stored calcium. Meanwhile, DAG stays behind in the membrane to activate protein kinase C. This powerful pathway drives smooth muscle contraction and secretions, and it gets activated by alpha-1, histamine H1, and muscarinic M1 and M3 receptors.
Okay, part 4. Second messengers and amplification. The big question here is, how do these tiny initial receptor interactions actually translate into such widespread cellular changes?
Well, it all comes down to the second messengers. These are the high-yield molecules you must have memorized. We've already talked about CAMP, IP3, and DAG, but you also really need to know about CMGMP. For instance, nitric oxide activates guanylyl cyclase to form CMGMP, which leads to profound vasodilation. That specific pathway is the exact target for drugs like nitrates and sildenafil. And never forget that calcium ions themselves act as incredibly vital messengers once they're released by IP3.
Now you might be wondering, why does the body use this incredibly complex relay system instead of just a direct link? The answer is signal amplification. Think of it like one tiny key turning on a giant machine. A single drug molecule binds to just one receptor, right? But that one receptor can activate multiple G proteins. Then each of those G proteins activates an enzyme that pumps out thousands of second messenger molecules. This snowball effect ensures that even trace amounts of a drug can trigger a massive, whole-cell physiological effect. It's brilliant.
Moving right along to part 5, enzyme and nuclear receptors. We're shifting gears now from the lightning-fast pathways to the body's slower, long-term cellular regulators.
For enzyme-linked receptors, specifically tyrosine kinase receptors, your absolute magic exam buzzwords are dimerization and autophosphorylation. Make sure you write those down. When a hormone like insulin binds, two receptor molecules actually pair up together. That's the dimerization. They then phosphorylate each other, which triggers a huge intracellular kinase cascade. This is clinically massive in oncology, by the way, because drugs like imatinib specifically inhibit these tyrosine kinase. You should also briefly mention the JAK-STAT pathway here, where cytokine binding activates JAK, which phosphorylates STAT, which then moves straight to the nucleus to alter gene transcription.
Conversely, our type 4 nuclear receptors deal with the lipid-soluble heavyweights, things like steroids, thyroid hormones, and vitamin D. Because they're lipophilic, these drugs just bypass the cell membrane entirely. They don't even bother with surface receptors. They cross straight into the cell, bind to receptors inside, and migrate right into the nucleus. There, they actually interact with DNA to rewrite mRNA and protein synthesis. Since building brand new proteins takes quite a bit of time, this perfectly explains why steroids have a slow onset but a profoundly prolonged action that lasts for hours or even days.
Finally, we've reached part 6, regulation and exam summary. Let's explore how the body protects itself by putting the brakes on this giant machine, and then we'll lock down your exam strategy. Exam alert, you absolutely must mention receptor regulation to get full marks. When a receptor is continuously bombarded by a drug, it adapts. Desensitization happens super fast when specific receptor kinases phosphorylate the receptor, physically decoupling it from its G protein. It basically becomes non-functional, and it can even get pulled inside the cell. That's internalization. This beautifully explains clinical phenomena like tachyphylaxis or building a rapid tolerance to beta agonists. On the flip side, the sudden withdrawal of a blocking drug can lead to upregulation, which is exactly what causes beta blocker withdrawal syndrome.
All right, let's bring it all together. To lock down all 25 marks on that essay, mentally map out one single massive flowchart. Start with a crystal clear definition. Compare the 4 families using a table to show their structural differences and speeds. Then spend the bulk of your essay really detailing the GPCRs, specifically drawing out the GS, GI, and GQ cascades. Define the role of your second messengers, hammer home the concept of signal amplification, and close it out by explaining receptor desensitization. And hey, make sure you give drug examples for every single step.
As you hit the books tonight and prepare for your exams, I want you to keep this one thought in the back of your mind. How does the unique molecular structure of each individual receptor ultimately govern the timeline of human healing? Because whether it's a millisecond flash from a GABA-A receptor opening up or days of altered gene expression from a steroid, it all comes down to the beautiful, incredibly complex architecture of signal transduction. Thank you so much for joining me in this explainer today. Keep drawing out those flowcharts and you are going to absolutely crush this pharmacology exam.